I want you to meet Sally. Sally is a lead engineer at Munder Diffling, a leading provider of paper and other stationery products. She's been there from the very beginning, one of the first engineers I hired. Because of that, she knows the code base inside and out, and she's extremely familiar with the issues of running it up in production. And Sally is sad today. Again. And she's sad today because their queues are sad today. Again. So she deals with the problem again, makes the system happy, then goes back to her normal work. She's still thinking about it, though. This has been a problem for years. And no matter what they tried, they never seem to be able to fix it. The next morning, though, after a good night's sleep, Sally wakes up with a solution. A radical new idea that will solve these problems once and for all. But to understand how this will solve all of her problems, we first need to get to know a little history and understand how Munder Diffling got here in the first place. First of all, though, hi, my name is Daniel, and I work at Indeed Flex. We're a flexible staffing platform based in London. As you probably noticed, though, I'm not originally from London. I come from Argentina, so in case you were wondering, that's the accent. And now let's go back to our little paper company. You see, when Sally joined Munder Diffling, they were a tiny team of only 3 developers. And they wrote the whole app that was running the entire company, buying paper, keeping track of the inventory, selling it, everything. And at first, everything was running in their one single little web server, and that was fine for a while, but after some time, they started having a little bit of trouble. So Sally decided to add a background job system. And then there was a queue. And the queue was good. It solved a lot of problems for the team. So they started adding more and more jobs to the queue. And then the queue was, still good. So more and more jobs got added. And so our story begins. A few months later, Joey receives a support ticket. Users are reporting the reset password functionality is broken. Joey takes the ticket, works in my machine, he says, and he closes it as can't reproduce. Now, of course, the ticket comes back with more details. Users are still saying they're not receiving the email, and sure enough, when Joey tests this again in production, he indeed does not get the email. After a little bit of investigation, turns out the job had 40,000 queues in it, and emails are getting stuck there and going out late. Joey spins up some extra workers so the queues drain faster, and he marks the ticket as resolved. But this had customer impact, so he calls it an incident, and while he's writing the postmortem, he starts thinking, how can we prevent this from happening again? Now, Joey knows that when a job gets stuck in a queue, it's because other types of jobs are getting in its way. And one way to fix that is to try to isolate those loads so they don't interfere with each other. We can't have all the jobs in one big bag and just pick out that in order, right? Some jobs are more important than others. Now, in some queuing systems, you can set priorities for your jobs. And that is some jobs like skip the queue, if you will, and run earlier. And Joey thought that might be a good idea, but it turns out their queuing system doesn't support priorities. Jobs are picked up in the same order that they put in the queue. As an aside, by the way, that's a good design decision. Priorities are not going to solve this problem, and we're going to see why later. Instead of priorities in this system, what you need to do to isolate your load is to create separate different queues. So Joey creates the high priority queue for more important jobs, and because programmers love us some symmetry, he also creates the low priority queue for less important stuff. A few days later, he actually finds some jobs that need to run every now and a while, but they're not urgent and they take a little bit to run. Be a shame if something important was late because of them, so he puts them in the low queue. A few months down the road, and Joey is dealing with another incident related to queues. Turns out everybody's jobs are important, so the high queue now has tons of different jobs, and now credit card transactions are being processed late because of some other jobs that is taking too long, and we're losing sales. And so after another postmortem, Joey christens the critical queue. And he makes it very clear to everyone. I know your jobs are important, but only very, very critical things can go here. We cannot let this happen again. I'm guessing none of you are surprised. Having some trouble with the clicker, I'm sorry. A few months later, the credit card company had an outage. And credit card jobs, which are critical, and they normally finish in about a second, were now taking a whole minute until they timed out. This started backing out the queue, and 2FA messages, which are also critical, started going out late. Again. But by this point, the company had hired a very senior engineer from a much bigger company, and she brought a lot of hard-won experience with her. This is Marianne. And when she noticed the incident, she recognized the problem immediately and got involved. Marianne had seen this exact same pattern before, and she knows what the problem is. Organizing your queues based on priority or importance is doomed to fail. First of all, there isn't really any clear meaning of what is high priority or low priority. And yes, there are docs with examples of what should go where, but they can never really predict all of the things that we're going to have to throw at our queues. Some of these jobs will also be very high volume or long running. And it's really hard to predict how all of them will interact. But she's seen this before, and she has the answer. We need to organize our jobs based on our different purposes, no priorities. That way, jobs that run together all look similar, making performance more predictable, and it's also going to be much clearer what goes where. That way, if credit cards start having trouble again, they don't interfere with unrelated stuff like 2FA, for example. And of course, you can't have a separate queue for every single purpose, although some companies have tried, but you can define a few for your most common things. Marianne sets up a queue for mailers, which are generally pretty important. But she also notices that we send millions of customer satisfaction survey emails, and those are not important, so she has a surveys queue, so they don't get in the way. A few months later, you have something like this, and jobs are humming along just fine. Every now and then, a new queue is born, and everybody's happy with this for a while. Now, fast forward a few years, and our little company has grown quite a little bit by now. We now have a couple dozen developers organized in different separate teams. In this case, following the different parts of the app. You have the purchasing folks buying the paper, the inventory people keeping track of it, the logistics team, etc. One day, the logistics team is having a little retro, and the math column is pretty long. The purchasing folks have done it again. This is the 4th time this happens this quarter. How many times do we need to tell them? That's how purchasing had this genius idea. Instead of calling vendors and asking them for better prices, they could just auto-email everyone and then let ChatGPT do the haggling. The feature was a little aggressive, and there were a lot of emails, so the tracking company didn't get the notifications they needed, and their shipments went out late that day. Again, it's not always purchasing, though. We had the same problem with the sales team doing the same thing too, right? And to be fair, we've also done this. Remember the ship-apocalypse last Cyber Monday where we clogged everyone's queues and we just ruined everyone's day? The conclusion seems clear. We have all these queues, but we have no control over what other teams are putting in them. And they don't know what our jobs are or what our requirements are for those jobs. There's only one way to fix this. Teams are supposed to be able to operate independently of each other. That's the point of teams. And just like that, the logistics team queue is born. Look, at least they didn't go for microservices, right? And of course, it's not just the logistics team that gets their own queue. They obviously share this idea with the other teams and ask them to do the same. And guess what? Not everything that the logistics team does has the same urgency. So 3 months later, we end up with logistics high and purchasing low. And of course, the original high and low and mailers are still there because there's hundreds of different jobs in there. Nobody knows where they go or what they should do. This is starting to get hairy. And also, it's a good thing that we have VC money behind this company, but even then, at some point, somebody does notice that we're spending way more money in servers than we should, and they start asking questions. Turns out we have 60 queues by now, which means 60 servers. Now, most of the servers are not really doing anything the majority of the time, but somebody has to serve those queues, so an obvious decision is made. We can configure processes to work several queues at once, grouping some of them together and reducing the server count. And guess what? Now, you may be wondering why I'm telling you this facetious story about people making very obvious mistakes. But the truth is, this isn't fiction at all. I've renamed the queues and the teams to protect the innocent, but I've seen this same exact story develop in exactly the same way in every company that I worked in. Hell, I've been half of these characters proposing things that actually weren't going to work. That was me with some of these bad ideas. But I've seen this enough that I think this is a common progression that companies go through. You may have seen this too, and hopefully the rest of the talk will help with those issues. Or if you haven't gone down this path yet, hopefully it can prevent you some headaches. The reason I think it's a common progression, by the way, is not that these characters are bad engineers. The thing is, when we're faced with these challenges, these steps do seem like the obvious solution. They make sense, and they solve the immediate problem. But the issue is that queues have interactions or behaviors that are really hard to predict. And so it's very hard when we propose one of these changes to fix a problem to predict what's the next problem that they're going to cause. So how do we get out of this? Well, we first need to think about what actual problem we're trying to solve when we start making new queues. Because the problem is deceptive, and we tend to attack the wrong issue. The problem isn't queues, and it's not jobs or priorities or threads. The problem is the language that we use to talk about this, which it often is. If you think about it, you have jobs running in the background all the time, and no one notices. If someone notices, that's when you have a problem. But what is it that people notice? A job didn't run. Which generally actually mean it hasn't run yet, but I feel like it should have by now. Or put another way, a job is running late. And here's the trouble, right? Here's where we start with the problems, because what does late mean here? Many, many jobs don't get to start running immediately when you put them in the queue. They tend to wait a little bit, and no one notices. Some may wait for minutes, and no one notices. Some others is very obvious if they're even a little bit late. For example, you probably know this one. You send a message to your friend, and the app will tell you when it's reached their phone. That took a second, and you didn't really notice. But let's try a different scenario, right? You probably know this one. You send a message to your friend, and the app will tell you when. How anxious are you getting right now? Is he in a tunnel? Did his phone run out of battery? Should I be worried? Is he okay? Oh, thank God he's okay. That job was late. So here's the issue, right? There's an expectation you have for your job, so how long it will be until they run. But generally, that expectation is implicit. It's one of those, I'll know when I see it kind of things like this, where you know that it's running late, but if I ask you when you think that that time is, you probably can't tell me. Like you got the database maintenance queue, right? Where you run a vacuum analyze for every table every night, because there was a problem with the statistics 2 years ago, and we'll never trust the database again, and that's running 20 minutes behind. Is that a problem? Not a problem. But what if your critical queue is 20 minutes behind? That's definitely a problem. What if it's 2 minutes behind, though? Is that okay? What if the low priority queue is running 20 minutes behind? Is that bad? The problem is the language that we use to define these queues and the job that we put in them. We give them vague names, and it gets us in trouble. Because low priority, high priority gives you a relative idea. This job is more important or urgent than that one. But it gives you no idea as to whether your queues are healthy at any given point until somebody's missing some job and they start shouting. And as an engineer, it also gives you no indication as to where you should put things. So what do you do when you're writing your job? You look around the queues for something similar and you follow that, or you guess, you listen to your gut about how important this feels. The problem is the words that we use. High and low priority doesn't really give you anything very useful. They're vague names. But the good thing is the answer is also in this language. Because what we care about is, again, not the priority, not the importance. It's not what team owns these jobs. This is what we care about. A job is running late. The one thing we care about is latency. And that's how we should structure our queues. We should assign jobs to queues looking only at how much latency they can tolerate before it feels like they're late. And that's the problem our friends are having, right? They're trying to isolate their workloads from each other, but they're not really designing their queues around the one thing that we care about. Remember, the symptom is always, this thing didn't happen as quickly as it needed to. The one thing you care about is latency. And that sounds simplistic, but I'm dying on this hill. Latency is really the only thing you care about for your queues. Everything else is just bonus. Now, there's other things you will care about to achieve that latency, right? Throughputs, thread counts, hardware resources, etc. But these are a means to an end. You don't really care about throughput. What you care about is that you put a job in the queue and it gets done soon enough. Everything else is just how you cope with the volume to make sure that happens. So separating our queues based on priorities or per teams, they're just roundabout ways to try and get that latency under control. But the issues, they don't center on the problem. They don't attack the problem directly. They're just roundabout ways. But to be fair, the very first approach was doing roughly the right thing. The high and low queues were trying to specify the latency tolerance for our jobs. The problem is that while this decision comes from the right instinct, having high and low and super extra critical is still super ambiguous for two reasons. First, you have this new job that you just wrote, and it's okay if it takes a minute to run, but not 10 minutes. Where does that go? Is that high? Is that critical? And second, when things go wrong, we want to find out before our customers do and they start calling us. So we want to set up some alerts. But at what point do you alert? How much latency is too much for the high queue or the low queue? And that's where our hero, Sally, comes in with her brilliant idea. We'll organize our queues around different allowed latencies with clear guarantees and strict constraints. Now let's unpack that a little bit. First, we'll define queues around how much latency a job in those queues might experience. That's the maximum latency we will allow in those queues. And allow may sound naive, but you'll see what I mean in a second. What's important is that you know that if you put a job in those queues, it will start running in no more time than that advertised maximum latency. We will name these queues based on that, clearly and unambiguously. Anyone that's looking at a queue needs to know exactly what they can expect from it. Now, here's the important part. That name, that's a guarantee. It's a contract. If you put a job in one of these queues, it will start running before that much time elapses. If a queue's latency goes over what it says in the name, alerts go off, fire departments get called, on-call engineers get woken up, and we fix it. That name is a promise, and you can count on it. And that part is the key. So as an engineer, whenever you're writing a job, we will choose what queue to put it in based on how much latency it can tolerate. And what that means is, what's the point where if the job didn't run by then, somebody will notice, and they will think that the job is late, or it didn't run, or the system is broken. And that makes it much less ambiguous way to put things. What happens if this job that you're writing runs an hour later? Will anyone notice? No, cool. Just put it in the within a 1 hour queue. So 1 hour too much, how about 10 minutes? Can you wait 10 minutes? Put it in the within 10 minutes queue. If not, it's within 1 minute, right? And granted, finding this threshold will be easier for some jobs than others, but you want to try and map out what are the consequences of running at different levels of late and figure out what will go wrong at each one. And the important part here is being realistic. There's always a temptation that everything needs to happen now. But remember that it can't all happen instantly, and we need to be thorough in figuring out how much time we can allow our jobs to wait, and always choose the slowest queue possible, the one with the highest latency guarantees. Now, maybe you're not totally convinced yet. So let's look at why this solves these problems in a bit more detail. The key thing here is that the names that we give these queues are clear promises. They're a contract, like I said before, and they set clear expectations. And by putting a given job in a given queue, a developer is also telling you what those jobs' needs are. Remember we said earlier, the problem is that jobs have an implicit amount of delay they can tolerate. That's a requirement that jobs have, and it's not documented anywhere and is not actionable in any way. When we set up our queues like this, you turn that implicit requirement into an explicit one. If your job is in the within 10 minutes queue, you know it needs to start running in 10 minutes or less, or else. Another side of this is that when you have things like high and low priority queues, you will be unintentionally mixing jobs that can tolerate different levels of latency. If your high priority queue is running, I don't know, 3 minutes late, that may be fine for some jobs, but not for others. And it's not really very clear what you can do with that. When you set clear expectations, it's much easier. You already know that all the jobs in the within 10 minutes queue can tolerate up to 10 minutes of delay. If your queue is running with 5 minutes of latency, you absolutely know it's fine because the authors of those jobs explicitly told you by putting them there. And this solves another one of our problems, right? We want to have alerts for our queues, and we want to have good metrics. We want to know if things are broken before the customers start calling us. But how do and if we breach one of these guarantees, you want on-call people to get paged, right? When you have names like high and low priority for your queues, how do you set a threshold for these alerts? How do you know that any threshold that you set is good for every job that exists in that queue now or that will be added in the future? When you have clear queue names, the alerts pretty much set themselves. Within 10 minutes queue, you alert if you hit 10 minutes and you're done. And of course, if your alerting is too late, we want to try and ideally prevent things from going wrong. You also don't want to waste too much money by having too many servers idle all of the time. These clear promises make it easy to do auto-scaling and set adequate thresholds for your auto-scaling. You know precisely what level of latency is acceptable, the queues tell you. You have an idea of how long your servers take to boot up and start helping with the load. You add a bit of margin, and that's your auto-scaling threshold. When you hit that much latency, you start gradually adding servers. And in this Flex, for example, we use 50% for most of our queues. If you hit 50% of the allowed latency, we start adding server, one more every few minutes, until the latency goes back down below 50%. And 50% was an easy number to choose. It was a bit arbitrary. We can probably tune that up a little bit for the slower queues. But the truth is, it's high enough that most of our queues run with a minimum number of servers most of the time. And when we get spikes, the system just deals with it. We almost never get paged for breaches. Oh, by the way, if you're ever going to do auto-scaling on queues, it's always based on queue latency. Never the number of jobs pending in the queue or anything else. It's always based on latency. Now, there's a flip side to this. These guarantees don't come for free. This is how it always works, right? Contracts always go both ways. And for us, that means just one simple rule. If you're on a queue that can only tolerate very small amounts of latency, you need to finish running pretty quickly, or you're going to basically ruin it for everyone else. That's the flip side to this contract. I call it the swimming pool principle. In a swimming pool, you normally have the fast, medium, and slow lanes, right? And if you want to be on this lane, you better swim at least this fast, or you need to move to a slower lane so you don't get in the way. In practice, this also applies to our jobs. If you are on a slow queue, where jobs can tolerate quite a good amount of latency, you can run for a while and it's fine. But if you're in a fast queue, where jobs need to start quickly, you need to get out of the way fairly fast, or again, you're going to ruin the party for everyone. When you put your job in a given queue, you're signing into that contract. And if you break the contract, you're going to get kicked out of the queue. So we need to set a time limit for the jobs that run in each of these queues. That is, if you want to be in the within 1 minute queue, you need to finish in this many seconds, or we can't take you in here. Sorry, you have to go to a slower one. And to see why, there's a bunch of queuing theory formulas to calculate this, but that's kind of boring. So picture this instead. You have a queue here on the left where all of the jobs need to start within 1 minute. And in like any queue, you have on the right the number of threads that are working those jobs, and the queue is running its little jobs, and they get out of the way pretty quickly. New jobs arrive, and everybody's happy. But I want you to imagine what happens if you take this queue and you start adding jobs that each take 1 hour from start to finish. What happens then? Well, as soon as one of these threads gets one of those long-running jobs, the thread is gone for an hour, can't pick up any new jobs. So a very small number of these long-running jobs are going to clog all of the threads in the queue really quickly, and you can't get any more work done anymore. If you try to do auto-scaling to solve this, you're going to be adding a new thread for each long job that you have. That's going to be a lot of servers. And that's why you want something like this, right? You want a queue where the jobs finish quickly. You can have a single thread handle lots of jobs, and more importantly, once they finish one, they can pick up the next. Things keep moving. And this, by the way, is also why having priorities doesn't work. Because your low priority but long-running jobs are going to easily clog all of the threads, and then there's nobody left to pick up the high priority short-running jobs. I want to say that again, because normally I just pass over that point, but we have a new big player in the queue running systems, and it does support priorities, unlike Scikit, and you really shouldn't use them. Because if you're trying to get your high priority jobs to have a higher priority, as long as they take a bit long to run, they're going to clog all the threads, and you're going to be back in the same problem, particularly if you're doing HTTP calls. So you need to set time limits for each queue, right? The faster the queue needs to run, the faster you need to finish. Now, where you set this depends pretty much on how much money you're willing to spend on servers and also on developers. It's a trade-off, right? If you set these limits too high, you let the jobs run for a long time, that's going to make the developers' lives easier, but you're going to need more threads, you spend more money on servers. If you set them too low, jobs that need to run with low latency need to be optimized more, refactored, maybe split into different smaller parts. It's going to be more annoying for your developers, and you're going to spend more time doing that instead of shipping features. You'll spend more money in developers. It's a balancing act, and it depends on your priorities. I like the rule of thumb of setting the target at 1/10 the latency limit. So a job within 1 minute needs to finish in about 6 seconds. A job within 10 minutes can run for up to a minute, etc. In reality, this is kind of aspirational. You're not going to start here, and it's also where you set them is going to vary a lot based on the current state of your app and your code base and what your needs are. It's quite possible, though. You're going to have to set this much higher at the beginning, spend more money in servers for a while until you can get them down over time. Now, there are 3 important things that you need to remember that are going to be key to this implementation. Number 1, the latency promise in the queue name and these time limits, again, are a contract between the infrastructure and the developers. And like any contract, we need to know if it's broken. If a job is going over these limits, a warning should go out to the respective team to either improve this or move it to another queue. This is not a page, shouldn't wake anybody up in the middle of the night, but it should make it clear that it needs to be changed. Number 2, there's an implicit social contract here. Remember the inter-team fights that we had where everybody wanted to have their own queue for their team? This is how you prevent that. If a job is breaching time limits, there needs to be an explicit permission for folks to move it. And of course, we will all talk to the respective people involved and get an idea of what's the best course of action. But if a given job is making queues sad for everyone, you need to have that explicit permission for other teams to move it out, or you will end up again in a situation where every team wants to control their own queues. And finally, respect the principle and focus on latency tolerance. Just because a job finishes quickly and can run in the fast queues, it doesn't mean it should. There's going to be a temptation to always put jobs in whatever the fastest queue is that will take them. Don't do that, because you may have jobs that can run very quickly, but nobody cares if they're late. Put them in the slow queues. Don't let them get in the way of things that are actually sensitive to latency. And this is how you solve the problems that you may be having with your queues. But wait, Daniel, I hear you say, what happened to our merry band of software developers? Well, after her epiphany, Sally proposed her idea to the team, and they liked it, and they started work on adopting it. Wasn't easy. certainly wasn't quick. But they got there in the end, and there are actually really useful lessons in how they did it. First, of course, they created the new queues with their alerts. And the rule was that every new job from now on can only go into those new queues. They actually made a custom Robocop rule to make sure that nobody would forget that. And then they started a huge task of sorting through all of the existing jobs and figuring out where they should go, which it's a lot. And it can be a bit daunting. But they found a very clever strategy. First, they started not with the most important things, but with the easiest. For example, some queues can be pretty obvious. They had 2 different queues that run overnight maintenance jobs. That's easy. Nobody's in a rush for those. They go in the within 1-day queue. Jobs that also took really long to run, for the most part, they also just got sent to the slow queues. Nobody expected them to run quickly anyway. And then once the easy stuff is moved out, there's no point in having all of these different queues for the different teams. You can just collapse them back into priorities temporarily, maybe add a few servers to them. You're still coming out ahead. And pretty quickly, those 60 queues turned into 9. And that was a massive motivational push because A, it was so much easier to keep the system running with all those fewer queues, but more importantly, they could see real progress. They had momentum. They were so eager to do the rest. Now, the next trick, that was really clever. They went for the jobs that run the most often, the highest volume ones. These are always a candidate for ruining your day, so you want to make sure that they're in the right queues. And these are sometimes harder to categorize, but there's normally not that many of them. And as they kept going down this list, at one point they realized that they had a lot of different jobs left to do. There was a lot of work still. But the total volume of those jobs that had left, it was tiny compared to the rest. So here's a little secret. They never actually finished. After a while, the jobs they had left were so few and so quick that there was very little chance that they would cause any problems. So they just shoved them all into default and left them there. It wasn't worth cataloging each one, which left them with this. Now, this was bliss. It was a dream to keep it running day to day, but they weren't done. You see, to move faster and keep momentum, they did take a couple of shortcuts. First, what I mentioned earlier. Those speed limits, they just set them way higher at first and just threw more servers at the problem. That made it much easier to start putting jobs in the right places and not have to worry too much about the performance. But now they had a clear list of trespassers, jobs that were too slow for their queues, which they would then work on, gradually making them faster and then gradually lowering these time limits until they got to the sweet spot. They also learned an important lesson: when to break the one rule. You know how I said latency is the one thing you care about? That's true, but sometimes there are some practical considerations that means it makes sense to stray from the path a little bit. For example, some jobs may need special hardware. Generally, in Ruby, this means a lot more RAM. If you can put them in their own queue, then you can have a few big, expensive servers for them instead of making all of the servers for that queue more expensive. Sometimes you have jobs that want to run one at a time. And that's generally anti-pattern, but there are actually some legitimate reasons to do this. Having their own queue with one thread and never more than one server lets you do that. And the name makes it clear you should never give that more than one instance. Some jobs do a lot of waiting on I/O, use almost no CPU. Mailers are like this, webhooks. You can have really high thread counts for those and save money on servers, but that would hurt the other jobs in the queue. Giving them their own queue lets you make that distinction and save some money on servers. You see, these are all the usual trade-offs of money versus complexity, and as always, your mileage may vary, but it's sometimes useful to stray from the path a little bit. Just make sure all of your queues still have a clear latency guarantee in the name, the usual alerts, and you're golden. And that's how our merry band of software developers solved all of their queuing woes, reached pure production bliss, and lived speedily ever after. The end.
Okay.
Now, before I go, I want to leave you with a couple of notes. One more minute.
Sure.
So,
go ahead.
I mentioned some of the most important lessons that our friends learned implementing this, but there are a lot more, and they don't fit in half an hour. You can get much more practical advice on how to do this on this repo. If you're going to take one photo, it's this slide. That repo has the slides from the thing, the whole script, but also a whole lot of other considerations, particularly how to monitor these. I also want to do some thinking. First to Tekin Suleiman, who wrote one of the best docs I've ever seen, and whose style I massively, I don't want to say stole, but definitely inspired this doc. If you haven't seen this, you should definitely watch it. And also my friends Nick, Lisa, and Chris for watching early versions of this talk and every other talk and making them much better. And last but not least, Neil Chandler, one of my colleagues who came up with most of those clever ideas that we saw at the end on how to make this tolerable. And that's it for me. Thank you.